Okay, continue. Okay, thank you. Yes, so today I just wanted to give a presentation. Maybe some parts will be a little bit general, be about earthquake risk assessment, and in particular this global model that was developed at the end of and released at the end of 2018. But then I would actually like to extend this a little bit about what's next now that there's this model exists. It has been refined for some parts of the world, but what else can we do with it? And what are some of the challenges that we've been hearing at GEM, but also through some publications and discussions with some of our partners? So in terms of what's earthquake risk assessment, I think, the vast majority of the people in the call will know this, but it's basically when we have an overlap between seismic hazard exposure and vulnerability. And usually the outcome is that these risk studies allow us to understand average general losses, probability of damage, the risk that some facilities might be closed, injured, fatalities, and so on. So just before I go to the details of what's earthquake risk assessments, a lot of people usually ask me, including my students, what is it used for? Why is this useful? Because obviously I think a lot of times in our mind, we're very much connected to the, we have to design buildings and we might do risk assessment for single buildings, but there is life beyond that. And I just want to give three good examples in my opinion. My favorite is definitely the one about the National Seismic Prevention Program for Italy. I think Italy, it's probably one of the most advanced countries, at least in terms of using science for their risk programs. And for example, there was this very interesting presentation from Dr. Mauro Dolce at the World Conference in 2012. And they were explaining how the funds, this 1 billion euros was distributed across the different regions in Italy based on the risk. So basically, and hazard. So basically you can estimate this and then distribute the funds proportional to the risk. It makes perfect sense, right? So despite the fact that 1 billion euros, you might think that it's a lot of money, the truth is that they estimated that it was 1% of what was actually necessary to basically make the country much better against earthquakes. But this is what was available. So it is quite important to make sure that the funds are distributed uniformly. Another partner, another global player that has been using a lot of science, a lot of risk studies to basically promote risk reduction is the World Bank, in particular, the Global Facility for Disaster Risk Reduction. There's been several projects supported by the World Bank where risk assessment is performed. This is just an example for a few cities in Eastern Europe and Central Asia. And you can see here that this allows us to identify what are the building classes which are more exposed? What are the building classes which are contributing the most to the losses, human and economic? And basically, those are the facilities that should be target of retrofitting techniques. And by the way, for example, for the country of Romania, a few buildings are going to be retrofitted already based on some of these results. The last result I wanted to give you, it's something that obviously you have heard about, which is the insurance coverage. And insurance penetration, it's very low in the vast majority of less developed countries. We can see here that almost only the Western world is following insurance policies and adopting insurance policies. And sometimes this is because they simply do not exist, in particular for natural hazards, because there's just not enough information. Or sometimes they do exist, but because the understanding of risk is not adequate, what happens is that a lot of these products are just not attractive. They're too expensive because basically the insurance providers want to protect themselves. So they will probably make some of these products a little bit more expensive than they should if they were to have better information. So with that, we understand that it is quite important for us to improve our understanding of earthquake risk for various regions. I'm only mentioning a few. So in 2009, 2010, the global earthquake model was funded, and the idea ultimately was to come up with the global earthquake model. And I would like just to mention about few of these components, also because most of them are publicly available, so they might be useful for your work, for all of you which are doing PhDs, master students, but also for the ones connecting to the industry. In terms of earthquake hazard, I feel like there's always two big schools of what you can do. Some people prefer earthquake scenarios, so basically estimating the losses from single events. Some people prefer probabilistic seismic hazard, where you basically consider all the possible events that might happen in a region with associated rates of occurrence. I will focus now only on probabilistic hazard for the time being. And what was done for this global seismic hazard model was a mosaic, was basically dividing the world in different regions, understanding what is the availability of different seismic hazard models. And this mosaic of 30 models was compiled and combined to come up with a global seismic hazard model. You can see here that some of the models were developed by national organizations, the ones with a remit to calculate seismic hazard for the country. Others were part of regional models, like, for example, the SHARE model for Europe, which is now being replaced by the SETA model. So, and some model, for example, for India was taken from the literature or part of regional programs. I will talk obviously a little bit more about seismic hazard, about how this model ended up in the end. But now if we move to the exposure modeling, this other component, which is about the buildings. It might look relatively simple because you could say, I can see the buildings, I can basically go building by building, collect information. There are various apps to do this. GEM has released one many years ago. OpenStreetMap also has a very interesting tool to do that. But if you think about doing this at the national, regional scale, it starts to become extremely complicated. Of course, you can basically then launch campaigns in which you have a team that goes building by building and collect information. This was an exercise done many years ago for the city of Pavia, where 1,300 buildings were cataloged using these tools. And you also have now a few cities, like, for example, Zagreb, which is extremely interesting for the purpose that Arash was mentioning before, that was affected by an earthquake recently. But some cities are building 3D models of their buildings, of their cities, which is obviously extremely useful. But I would like just to highlight that these initiatives, just like also this one, like OpenStreetMap, a lot of times they focus on information like the asset footprint, the use of the building, sometimes the number of stories. But a lot of the information that we need for earthquake risk assessment, it's just not there. Like, for example, when was the building constructed? What is the main construction material? What is the lateral load resisting system? Irregularities, changes in the building. So this is all information that unfortunately is not always covered by this data sets. So because of this region, in order for us to go global, to make sure that we could cover the entire planet, we have to follow other data sets in the vast majority of the cases. Quite often the process follows 4 main steps. So we started by collecting all the information that exists on the housing census, socioeconomic data, the workforce, the population, dwellings, the type of dwellings, the land use of the country. And this is usually the first step. A lot of this information that is collected on a housing census, it was not designed by earthquake engineers. And a lot of times it was not designed for risk assessment. So because of that, it is also necessary to do a lot of surveys. And we launch a lot of surveys, a lot of online surveys where we ask people, how are the buildings in your country? How are the regulations? Several questions to understand how is the building stock? Basically the information that is probably not covered by the housing census. For a few countries, this information is simply not available, or since the last housing census was performed, there's been like a few natural disasters. This is the case for Haiti, where the last housing census was done. And after there was the Haiti earthquake, and then 2 cyclones, category 5, hit the country. So obviously the data that was previously connected is probably not applicable. Moreover, some of the data that is collected on the housing census doesn't have sufficient spatial resolution. So we need to use satellite data in order to redistribute the buildings in the country to have a better modeling of the building stock. And finally, and this is probably one of the most important steps, is the validation part. And usually we do a lot of workshops, well, a little bit more before this pandemic. We went to a few countries, we show the model, we interact with the local experts to understand if the model is reliable or not. This is just a list of the countries and obviously cities where we organize these workshops where we basically bring people from different countries. We present the results and then we try to understand if what is being presented is reasonable or not. Are the costs too high, too low? Are we missing building classes? Is this model making sense? Are there other sources of information that we're missing? So this is usually the process that was carried out. And this is usually how it looks, the result. For example, this is just the example for Costa Rica. So we have number of buildings at the different administrative levels distributed across different building classes, and all of this with costs for the structural components, non-structural components, contents as well. Okay, and when you do this at the global scale and you also distribute the buildings spatially, then you can come up with something like this. This is the result of the global exposure model distributed on an evenly spaced grid with 0.3 by 0.4 decimal degrees. So moving forward now to how can we start combining already these data sets? Is this useful, having this information about the buildings plus the seismic hazard? Well, I think it is, even if before we bring, the complications of the vulnerability, even before we talk about risk, because it highlights already places where there's a lot of exposure and there's also a lot of seismic hazard. In this image here, the height of the polygon is the number of buildings, residential, commercial, and industrial, and the color indicates the seismic hazard. So warmer colors indicates higher hazard, and colder colors lower hazard. This is just a video showing how it looks for this part of the world. It's a little bit easier to show. We have, for example, New Zealand with some concentration, Indonesia, Papua New Guinea, Philippines, obviously Japan, and we can see the Himalayan belt over there with a huge concentration of buildings and still high seismic hazard. In contrast, we have parts of China, parts of India where the population and building concentration is high, but the seismic hazard is not that high. The same thing can be said by South America. We have obviously the usual suspects: Chile, Ecuador, Colombia, Peru, places with high seismic hazard and high concentrations of exposure. So there's obviously a huge correlation between places where we see high exposure, high hazard, and past destructive earthquakes. But there's also a few exceptions that basically we know that there is relatively high seismic hazard, also high concentration of buildings, but we didn't see a huge event in the past years. And this is also why this information can be used to raise risk awareness, but also to carry out studies like the one I showed previously, supported by the World Bank, to understand what is the potential for risk. On the seismic vulnerability, I obviously don't have much time to go over this component, and this component could be an entire lecture just about this. But basically, we needed to produce something that was going to be applicable for a lot of countries around the world, a lot of building classes. We needed to select a lot of ground motion records because we have very different tectonic regimes, very different failure mechanisms across some of the building classes. So what we did was we developed several single degree freedom systems, more than 500, representing different building classes, and we collected thousands of ground motion records from different parts of the world. And we just did nonlinear time history analysis on those single degree freedom systems. The result is a fragility function that can be converted into vulnerability functions for economic losses or for fatalities. The methodology is obviously relatively simple, but on purpose, because the idea is that as more information becomes available, we can basically adjust the capacity of the single degree freedom systems. We can use different damage criteria. We can combine this framework with different ground motion records. And all of this is open source, which ensures that if you want to bring your own models, your own capacity models, if you want to bring your own ground motion records, you can just plug your pieces and still have vulnerability functions. So if I move just now to the final part, so what is the result when we bring all of this together? So we use the mosaic of the 30 seismic hazard models to generate thousands and thousands of years of events. And this is what you see here. Every time that you see an image, this is a 1 year of seismic events generated randomly. So this is a stochastic event set, okay? This is just showing 50 years of those events. So this is obviously hypothetical, it's just 50 years. If I repeat this exercise, I'm obviously going to have different results. For each one of these events, we model always as a 3D rupture. It's never just a single point. From each one of these ruptures, we always estimate how much is going to be the shaking in the region for different intensity measure levels, because the vulnerability model uses different intensity measures. We bring the exposure This is just an example for Costa Rica, and we estimate the economic losses, okay, based on the vulnerability functions that I was presenting before. The result, and using Costa Rica once again, is average annual losses, problem maximum losses, annual probabilities of collapse for different building classes, for the residential building stock, for the non-residential building stock, also information about fatalities, injured, population displaced. So there's a lot of information that can be extracted from these models, as well as disaggregation of losses based on the regions, building occupancy, building classes, and so on. If we do this once again at the global scale and disaggregating for the world, this is what we can obtain. So basically, this is a uniform map of seismic risk globally. I would like to highlight something that is quite important, that despite the fact that the methodology is uniform across the world, obviously we cannot say the same thing about the risk metrics, simply because the quality of the data is extremely different. For example, countries like Portugal, like the United States, New Zealand, Australia, Italy, the level of detail on the data usually is quite good. And I would also say that the seismic hazard models also have a different level of detail. For other parts of the world, this is not true. So obviously, when we look at these maps, we have to understand that the uncertainty is different from region to region. So this model was released in 2018, and now what? So several efforts after this. So obviously on the dissemination and research. So in the first months of release of the model, if I'm not mistaken, there were more than 10,000 downloads, combined downloads between the seismic risk plus seismic hazard plus publications plus country profiles and so on. So obviously there was a lot of interest in these models, and a few users asking to use this basically more for risk awareness, but in some rare occasions also for risk mitigation plans in the country. Parts of these models have also been extended to urban risk assessment, for example, in some cities in Colombia, now also as part of another project for Ecuador, Dominican Republic, and again, Colombia. Some images that you see here, this is for Canada in Vancouver. So basically the model provides some ingredients. To apply them at the urban scale, we have to do more work. These results have been included in the Global Assessment Report from the United Nations. Also, some of these models are being ported into Oasis and Touchstone, in particular for countries where some models do not exist for the insurance pricing. So obviously less developed countries. Then also, part of another webinar, past webinar, I've showed that how these models then can be used also to support decision makers without the crisis. So basically understanding how an earthquake that happened in a place that has been affected by a pandemic, how the effects can be exacerbated. And finally, this model is also being used for some training, teaching material. Since the beginning of, well, actually last year, more than 200 people have been trained in order to use risk models, hazard models, using some bits and pieces from this global model as part of another project supported by USAID. This is something that we had to adapt because of the pandemic, but I think it has been quite successful, and we've seen a lot of interest from the community. So what now? Is this sufficient? Are we done? Can we all go home? Well, probably not. And this was actually something that maybe shouldn't have been surprising, but it was a little bit for me in terms of how insufficient the model that I just presented is. And a lot of these questions were not actually written by me, but they were asked by other people. So what are you guys doing about secondary perils? We've seen like a lot of the events, including the one from Indonesia, where liquefaction and landslide was a big issue, also in New Zealand, in some part of the United States. So clearly we are underestimating the losses in this global model. What about lifelines in critical facilities? What about the contribution from business interruption, which quite often, mostly in developed countries, can be way higher than the direct losses? Also, how can we make sure that these results can be used for decision making in the long term? So not just for today, but actually trying to understand how this can affect the future. What about the large uncertainty that we have in these risk metrics? And finally, is this actually helping us to do better scenario modeling? How can we validate these models? So Obviously, there's no time to go over all of these questions, so I would like to focus just on three topics. The first one is the secondary perils, which is something that we're asked a lot of times. We're missing a lot of the losses due to liquefaction and landslides, fire following, and tsunami. This is simply not covered in the current model. So we obviously try to understand how we can try to start incorporating this, the impact from these effects in the global model. And it's not that simple as expected. We have a very prototype, a very preliminary implementation of liquefaction hazard calculator in this OpenQuake engine, this tool supported by GEM, and we're almost done with the implementation of the risk results. The issues that we have is that the current models for liquefaction and landslide, so both for hazard and risk, are very limited. Some of these models were developed with data only from a few events, for example, in California, obviously some data now from New Zealand, some data applied more at the local level in Japan, but the models have a huge uncertainty. For example, this model was applied here in Portugal, and we can see that depending on the model, we have very different results. So it's complicated to produce something knowing that the uncertainty is so high. So in my opinion, I think this is still a challenge, and there's still a lot of work to be done in order to estimate liquefaction at the regional scale. We also have the issue of geotechnical conditions. We need to understand a lot about the soil, the water table, saturation, the slope in the different regions. And some of these data sets are simply not available. There are a lot of microzonation studies at the world, but usually this is only for portions of a city. Sometimes they don't even cover the entire cities. And finally, obviously, we have also the problem of exposure. We don't know a lot of times where the buildings are located. So we have to also improve our exposure data sets to make sure that we are putting the buildings in the right location. Because putting a building in this location or 50 meters on the side might mean that the building is destroyed by a landslide or not. So this is some of the challenges that I think we're going to have to overcome. But I think information like, for example, with big data, now that we have data sets with 30 meters resolution or even more, are allowing us to understand where buildings are located. For example, for all of the European capitals, the Copernicus program from the GRC, from the European Commission, is providing information about the building footprints, but also the height of the different buildings. And this can obviously improve a lot our risk estimates. The other problem that I wanted to talk is about this need for us to provide risk information to decision makers. I think that's probably one of the final goals is to do that. But how can we make sure that what you produce today is also useful in the future? I think a lot of you have heard about this Sendai framework for disaster risk reduction. It's a framework, so it's basically an international agenda. It's an agreement by a lot of the countries that it is necessary for us to lower risk. And they also gave some targets, and a lot of cities, sometimes even cities, are putting their own targets about how much they want to reduce the risk. But the problem is, if you calculate the risk today, maybe you are even below that target, or maybe you are very close to going down that target. But with the increase in the population, increase in the building stock, and also increase, for example, in the vulnerability due to incremental construction or lack of maintenance in the buildings. Or, for example, if you think about meteorological hazards, which are increasing due to climate change effects, we might have this trajectory in terms of the risk. It might be increasing. Moreover, let's say that you're aware that the risk is increasing and you're going to pursue a given mitigation program. Maybe it is retrofitting buildings, better urban planning, and also improving insurance coverage in a given country. Maybe that's still not sufficient for us to understand if we're going to meet given targets. So there's the need for us to try to predict the risk for the future. So this is actually not that new, and this is just a Google time lapse of how the cities have been expanding. And what I wanted to show is that a lot of times we're talking about a time frame of only 30 years, okay, sometimes even less. And you can see how some of the cities in the world have expanded so much. Also, something that you can see from these videos is that this expansion, it's not random, right? You can see there's a pattern. So basically, urban places, new areas of build-up environment are attached to other urban areas. You can also see that The location of roads has obviously a big impact. Sometimes the proximity to water bodies. So there's a lot of factors which are influencing where we're going to put buildings in the future. We've seen this by looking at the past, and we can expect the same thing for the future. So in order to try to understand how we can model this, how we can start modeling losses into the future, how we can make decisions into the future, understanding how the cities, how the countries are going to evolve, we did a few exercises, mostly located in Central America. I wanted to show here an example for Costa Rica, the great metropolitan area of Costa Rica. So there's a lot of satellite data now. These are huge data sets which give information, sometimes for some countries at the 30 meters resolution about the built up area. So basically when certain parts of the country were built. And this is the four main eras that it gives you: 1975, 1990, 2000, and then 2015. So we have these records of how some of the cities have been evolving throughout time. We also know that this is not random. The expansion of the cities is not random. It depends on the proximity to amenities, roads, towns, sometimes the slope, sometimes also the elevation, and also water bodies, national parks, highways, cities. So there's a lot of environmental and man-made data sets. And all of this nowadays is available because of initiatives like OpenStreetMap, also all the work that NASA does with the digital elevation model. So these are all data sets that we can basically collect almost at the global scale. So by doing that, we actually develop a multi-agent system model that allows to understand how the city is evolving. Here for the San Jose, the capital of Costa Rica. So what you see here, it's basically, we provide all the previous data sets that I showed you to this model. The model learns how basically the city has been expanding based on this auxiliary data sets, the man-made and the natural data sets. And then we can start doing some predictions. Now let's try to repeat how the evolution in the country was observed. And this is just an example for the city. So once we learn how to do that, then we can actually start predicting how the city is expected to evolve into the future. And this is what we see here. You can obviously tell me, but there's so much uncertainty, right? There's so much uncertainty about, urban planning, the regulations and all that stuff. Also how the population is expected to increase. This is obviously tied to the population. Central America and South America, Latin America is well known for having a huge urbanization and also increase in the population. But these are all sources of epistemic and aleatory uncertainty, which can actually be introduced in the model. So the result is this. In the end, you don't have just one trajectory of how the risk is expected to vary in the future. You have a range because we need to propagate all these sources of uncertainty. But this allows us to understand this is the current trajectory of the risk for the country, or this is the estimated trajectory of risk for the country. Now, I obviously don't have time to go into detail on this. I just wanted to say that the fun part is actually not so much predicting the risk, but it's actually now introducing risk mitigation measures. What if we start retrofitting 10,000 buildings per year in the country? What if we improve the design regulation? What if we start discouraging certain building classes? What if we start making sure that people do not build too close to soft soils and active faults? So all of this information can be introduced in this model, and then you can start seeing different trajectories of risk. And finally, you can find which one is going to take the risk to a value that it's lower than what you're willing to accept. So the final thing that I wanted to mention is this part about validating models and scenario modeling, which is something that obviously we hear a lot of time. So on the scenario modeling, I'm no longer considering the millions of events that were stochastically generated. And instead, I'm considering, for example, just a single rupture and the consequences of that single rupture. Once we finish, actually, while we were doing this global risk model, we had dozens of people asking us, how does that compare against past events? Have you compared your model against past events? The answer is yes. We did a lot of scenarios. We obviously simulated more than 100 events that happened since 1980. And then we tried to understand, is our model actually predicting well the losses in the past or not. These are some results in terms of the estimated damaged buildings or also estimated losses. You might think that this is actually giving you a good trend, a good results, but not so much. Remember that these plots are in the log scale. Okay, so you can see that a lot of times we are missing the losses that were estimated by one order of magnitude. So instead of being, for example, 10 million, only 1 million, which is obviously a huge difference. So it's obviously something that we have to understand and try to improve. Some of the reasons behind this is, I don't know if I want to say limitations, but it's just basically that we did a lot of tests to understand the main sources of uncertainty in this scenario modeling. And the main sources of uncertainty usually comes from the shaking. We just don't know how much was the shaking. We can use ground motion prediction equations to estimate the shaking in a region, but the ground motion prediction equations have a huge aleatory uncertainty, okay? And if we don't know exactly which GMP you should use, then you also have epistemic uncertainty because we have to use a few. This is just an example for the L'Aquila earthquake. This was done many years ago, but you can see that depending on the GMP, you might be estimating 40,000 unusable buildings or only 5,000. So huge uncertainty in this estimates. Also, you could tell me, well, but if the earthquakes already happened, then there's recording stations. I will say maybe. For some of the events that happen, even some of them quite recent, there's just no recording stations. I can also tell you that for some of the events that happen, there's the recording stations do exist. Okay, for example, I'll tell you that for Ecuador, there were some recording stations there, but the data is often just not available for you to constrain the shaking, to constrain the ground motion fields. Okay, you might also heard about the shake maps from the USGS, which is probably one of the best sources of information for ground shaking after events. You can also see that a lot of times they do try to incorporate data from recording stations, but sometimes, despite the fact that the data exists, it's just not available for us to constrain the ground shaking. So because of that, in my opinion, I think in order for us to try to improve how we estimate the losses from past events, I think there's a lot of work that still needs to be done on the ground shaking estimation side. And I feel like the physics-based model is probably a way for us to reduce a little bit the uncertainty that we have there. But there's also very interesting developments in machine learning and artificial neural networks. Actually not new. Some of these models have now 10 years. And I think there's still room to continue using these models to lower some of that uncertainty. But still talking a little bit about scenario modeling, because obviously a lot of times, every time that an earthquake happens, and we were hearing Arash telling us before about the event in Zagreb, now also the event on the 14 about in Indonesia. So how can we make sure that we can predict these losses a little bit better once an event happens? The normal way is, of course, just applying a GMP. We have vulnerability functions, we have exposure data, and we can predict those losses. But as I showed before, there's a huge uncertainty there. And a lot of times we just don't have enough recording stations to constrain the uncertainty. So we've been trying to do something different, and with the support from the World Bank and a few partners, the GPL team at NASA, OpenStreetMap, and so on, and see if we can revisit using satellite imagery to improve the damage estimation. There are some work about this, of course. In 2010, there were already companies trying to use satellite data to estimate the damage. But I want to say that the detail in the satellite data has improved a lot, both in terms of the spatial resolution, both in terms of the technology, but also I can also say that in terms of how much time it takes for a satellite to go over a given region. I think it's by the end of 2022, it's always going to take less than 24 hours for us to have a satellite going over an affected region. So we try to explore this technology. So let's say if we have detailed data before the disaster, maybe coming from OpenStreetMap, maybe coming from municipalities like we've seen from Zagreb. Let's also assume that many teams out there, NASA is just one example, but there's many teams out there that after an event, they just release these damage proxy maps, which indicates the different pixels, what is the change in terms of the built environment. We can plug this into a machine learning platform because you can basically feed this platform with a lot of data from past events. And hopefully we can then identify the most impacted regions, distribution of damage, and also even triggering parameters. If you think about insurance policies, insurance products can be triggered by this technology. So that's exactly what we did. And we tested this with the Zagreb earthquake because there was a very detailed data because of that model that I was mentioning before. There was a lot of data here. And this was a good opportunity to try to train this machine learning platform. So we provide the location of the buildings, we provide what was the observed damage. We also provide some information about, we can also provide some information about the characteristics of the building. This was obviously not the case because some of this information was not available, but you can provide information about height of the building, when the building was constructed, is this building code compliant or not, okay? So this is all information that can be inserted into the machine learning process. And in addition, of course, we have to provide one of the main ingredients, which is this damage proxy map, is this satellite product that basically indicates in the city what are the parts would basically seem like there's been a lot of change in other parts where it seems like the building remains the same. So just to summarize the process, we have a given building and we can provide information like occupancy, number of stories, even information about the expected vulnerability. We can also do some filtering because a lot of times these damage proxy maps indicates regions that like there's a lot of change just because there was a lot of cars in the parking lot and now those cars are no longer there, okay? So you can also do a lot of filtering by location of buildings, but also using, for example, a shake map from the USGS, that if you see that the macroseismic intensity is extremely low, then we shouldn't expect damage to occur at that particular location. We also bring the damage proxy map and it's a damage grade. So let me just try to show you what were the results for this particular example in Zagreb. There's still obviously a lot of uncertainty, but we can see that in general, buildings that collapse, which is this damage state 3, and also buildings that did not have damage, the accuracy was quite good. And if you think that, you know, even when you send people into the field, if you want to characterize buildings according to, let's say, moderate damage or extensive damage, even going into the field sometimes is quite complicated because there's obviously differences of opinions between surveyors. So I would say that the model it's quite acceptable, even with all the limitations we had in terms of the exposure model and the limitations with the damage proxy maps. If you also think that perhaps for some of the actions that we want to take right after an earthquake, maybe what you want to understand is places which were not affected and places which were really affected, like for example, either the building was undamaged or it was damaged, then the accuracy of the model increases to 90%, which I think it's quite remarkable. So one of the limitations from using something like this is that you need to have extremely good pre-disaster data, which is obviously not available in a lot of places. And you also need to make sure that the technology, the methodology that is currently used to estimate this damage proxy maps from satellite data needs also to be slightly improved. So just to finish, some final remarks. Seismic risk assessment, I think it's now a mature field. I think it was not maybe 10 years ago, it was still in its early stages. Seismic hazard is a completely different beast. I think, you know, more than 40 years, we've seen seismic hazard maps and PSHA is well established, but I think risk was less mature, but we've seen more and more studies on the risk side, but it still lacks of widespread application. There's this global model, but if you try to search for studies at the city level, country level for other parts of the world, they're quite rare. So there's still room for improvement there. There's plenty of research on the damage loss assessment due to ground shaking. You know, every year we see papers about fragility functions, vulnerability functions, you know, new GMPs, but the impact of secondary hazards is often neglected. I'm not saying that excellent studies do not exist. They do, and we've seen a lot of great studies from Japan, from New Zealand, but it's not in terms of volume and probably also in terms of detail, it's not comparable with what we see on the ground shaking. I would also like to highlight that the studies that we're currently doing, we have to understand that if we really want decision makers to use the results of our studies for the next 20 years, for the next 30 years, and a lot of these investments usually are not for tomorrow, next year, it's for the next 30 or 40 years, 50 years, if you think about the life expectancy of buildings. So obviously we should try to understand how the risk is going to change in the future. And finally, I just wanted to, mostly for those of you who are doing master thesis and PhD thesis, there's a huge universe out there in terms of big data, using these huge data sets of satellite data, obviously OpenStreetMap, that can be used to improve our models. And machine learning is also fixing some of the limitations we have with the mathematical formulations on the vulnerability side and also on the GMP sides. So I think there's also room for us to explore these technologies there. And in fact, despite the fact that usually I say a lot of times that earthquake engineering, seismic risk, seismic hazard, is perhaps a little bit more advanced than the science we see on other hazards. But actually, I see a lot of these technologies already being heavily used for other perils, like, for example, flood modeling, even on some volcano hazard assessment. But I think there's not that many examples on the earthquake side, I guess, because a lot of times we get a little bit accustomed, a little bit used to use the same formulas, the same methods that we've been used and they've been working in the past years. But I think there's room for us to get out of our comfort zone and start exploring more these technologies. And with that, I want to thank you for this opportunity.
Thank you very much. Very interesting. I'm sure in a normal situation, there will be loud claps of hand, but representing all of those, I'll clap a hand.
Thank you, Arash.
Very interesting exposure models, those 3D exposures, very helpful. Very interesting that you managed to integrate the pandemic with your models as well, and predicting city expansions are mind-blowing. As always, if you're happy, we will have some few minutes for Q&A, but while people are thinking of their questions, can I ask that the Zagreb model, the machine learning of Zagreb's, let's say, structural damage, was it live? Like, can it be live if an event happens and then you see the calculation, or does it take lots of processing and like you need lots of information input?
Yeah. Thank you for the question, Arash. The idea, it's exactly that. When we were developing this was a project that was supported by the World Bank, and the partners were JBA, OpenStreetMap, the humanitarian OpenStreetMap, and the JPL team at NASA. And the idea was exactly that, was to try to develop this near real-time framework that basically, if something happens in the world, we know that basically we have the satellites going in less than 24 hours on the top of the affected region. Then we just have to produce this damage probability, damage proxy map, okay? And then basically you can have better risk estimates than what we do right now with GMPs and fragility functions. This was obviously a pilot project because it takes a lot of time to make something like this operational. But the idea from the World Bank was to estimate damage, losses, and even try to explore, can we actually trigger insurance policies based on this? Because there is already some products like that, parametric products that we can actually use for this. I can see that actually my colleague that was leading this activities, Anirudh Rao from GEM, is also on the line. But that was indeed the idea, that something like this can be triggered automatically after an event happens. Because the only thing that you need is, obviously there's a lot of homework, Arash, that you have to do, because you need to train. You need to collect extremely detailed model. But look at the detail of the data that we have now from Zagreb. I think this level of detail is going to be the same we will start seeing for future earthquakes, because now every time there's an earthquake, we send like 100 teams into the place and they collect information and the photos are on Twitter and we have all this databases of information. So I think, as more data, more images become available, we're going to see this models become more and more efficient. Maybe Arash, just to finish, I just wanted to say that Google and Facebook are actually also exploring some of this technology. We actually had a call with one of them when we were doing this model. I don't know if that technology is going to be something that will be made available to the public or if it's just something that will become a commercial product. But usually we know that when some of these organizations invest resources, something quite impressive comes out.
True. So no vulnerability, no fragility curve was used in predicting those damages. It's just image engineering.
Yes, no GMPs, no fragility functions.
Wow.
That this probably goes against everything we believe, but no vulnerability, fragility, GMPs, nothing like that was used to predict that damage. And as you can see, we managed to predict with a level of accuracy of 90%, between what was damaged and what wasn't damaged.
Okay, I'll ask a little bit technical question you might not know. There was an angle of the satellite taking the image, so it could see from different images, or was it like a Google Map bird eye view?
Then I don't know, Arash, because basically what we received from this team, from the JPL team, their program is basically pixels, and the pixels have a value between 0 and 1. 1 being this is completely changed, 0 remains the same, and then we have intermediate values. So I don't know exactly what was the the overall technology that they use, if they use also stuff from different angles.
Fair enough. If anyone has any question, please raise your hand. Feel free to unmute yourself. You can write it in the chat as well. I will read it out. One thing about that, yes, Roberto, please.
Thanks, Vitor. Your presentation was great as always. So talking about these machine learning models, which in the end become black boxes, it's very interesting that you are somehow pushing in this direction. So I'm sure you're not trusting this model, and you're not willing to trust these models with no check. So how do you plan to check the validators?
Thank you, Roberto. So Roberto, when I'm saying that, I think we should try to start using a little bit more of machine learning. Inside of machine learning, you have dozens of algorithms, right? So the ones that we've been exploring is, for example, artificial neural networks for the prediction of for example, structural response in structures. And those models don't have to be black boxes because, for example, in artificial neural networks, you know exactly the weights that you are applying, for example, on the different branches. But something that we've seen that improves a lot is, for example, we know that in our fragility functions and vulnerability functions, ultimately you have to come up with intensity measure, right? And some of them with that average SA gives something a little bit better than others. For example, using artificial neural networks, you don't have to make this decision. You can basically use all the intensity measure levels that coming out, let's say from shake maps or from GMPs, if you want to use that. And then you can use all the information that is coming out of the of this ground motion records to predict the structural response. We actually did a lot of tests comparing how vulnerability and fragility functions behave against artificial neural networks by using directly the results from dynamic analysis, and everything is better, using that in terms of sufficiency, in terms of efficiency, and also in terms of accuracy. So I think you have these two schools, right? You have the mathematical formulations, for example, the ones from the GMPs, where you know that each parameter, each component on the GMP has a physical meaning, right? And that's very nice. That's very beautiful. But I think you still see that for some combinations of magnitude and distance and VF30, we still get values which are very strange, sometimes very high, sometimes very low. And I think this is a lot of times because we are extrapolating these mathematical formulations to combinations of parameters that we didn't have the data there. And I think some of these algorithms might be able to not completely eliminate, I don't want to be naive, but at least to improve some of these limitations on the models.
Why don't we use it backwards? So if everything is better by using these methods, it means that there is some physical effect we are missing because we are not sensitive enough as humans to check it, because they check correlation, that they check patterns. If there's a pattern, the model works, and if there's a pattern and we don't see it, maybe we can use it backwards. I don't know.
Yeah, of course. And I think, what you're saying is obviously what we've been seeing, for example, with the physical models, where we don't trust that much some of the mathematical formulations. So we take a step back and we try to use the physical models, for example, to estimate the shaking. But ultimately, like, either we use always the physical models, for example, in rapid loss assessment, which is something that can be done, but depending on the model, it might take a lot of time. Or you can use the data that comes out of the physical models, which hopefully you're not missing that many, let's say, particularities there. And you can train, for example, this machine learning algorithms, which then can basically run in a fraction of seconds using the data that was produced by the physical models.
Yeah. Thanks a lot.
Thank you, Roberto. And I like your background.
A bit scary, but yeah. So if anyone else has any question, please raise your hand. Carmine, if you
well, more than a question, a comment. So thanks a lot, Vitor, for the great presentation as usual. First of all, I really like the idea of this, future projection. You may know we are working on a project which is called Tomorrow Cities. And I was supposed to talk to you for several weeks now. I mean, John Rees is on my, and I think we really should, because we are exactly trying to do, this modeling of future expansion and future developments in Kathmandu, Nairobi, Istanbul, and Quito. And so definitely it's much smaller scale. So it's, focusing on specific cities, and within those cities, specific urban plans. But definitely there is a lot of synergy there. So, and indeed, you will be one, you don't know, but I'm officially telling you, you'll be one of our advisory board member for this work. So I'll be in touch with more details. And and this is more a question. So I know you guys have done a lot of great work also on the social vulnerability side with Chris Barton, and how do you see these also being implemented from the impact side? So not just static social vulnerability in a sense that you have disaggregation of, I don't know, income, gender, age, whatever, but also really as an output. You may have seen the World Bank is working a lot on this concept of well-being losses, for instance, because the idea is, physical damage, especially if you are targeting urban poor. And so within the Sende framework is not the best proxy, because of course urban poor don't have much to lose. And so the idea to look at other proxy like access to infrastructure, or again, loss of income, loss of consumption. Is there any plan within GEM to also again expand the type of risk metrics more on that direction, or not yet?
Thank you, Carmine. It is indeed a very complicated question.
I know.
So let me try to divide that in 2 points. The first of all, yes, Carmine, I've been even very recently, and specifically for the World Bank, we had to estimate losses for all the European member states. And then they also have not just the direct losses, then they were like, oh, we also want fatalities and injured, because we also want to estimate the economic losses, because less people will be, available to generate wealth in the country. Yeah. So, and that was actually the first time, I have to admit, it was the first time that we had to do those calculations. It was very interesting, if you imagine about benefit cost analysis, because it increases the ratio quite a lot. But it was one of the first times we had to do that. And I don't think there's many studies out there about this. There's one from Abby for California, but I think that's one of the only studies that I've seen about that. Also, on the other part about the business interruption and long-term loss, it's obviously something that is missing on this global model, and it's missing in a lot of the studies that we do. We have adjusted this framework, this vulnerability framework that I was describing before, to also start estimating disruption time, and then it might be business interruption, but at least disruption time. And also by working with some of the insurance companies that are partner with GEM, we try to understand how much is the annual turnover to include that on the losses. But it's definitely something that we haven't made significant progress, in part, Carmine, because I think it's one of the things that GEM shouldn't come up with something new because there's already so much stuff out there. So it's more like a matter of trying to understand, what's out there and compiling in a way that other people can also use. But it's definitely something that we haven't done much work about, and we definitely need to improve that stuff. So I'm probably going to be looking at the outcomes from the Tomorrow Cities project, and then pleasurize part of the work.
Thanks. No, it would be great to collaborate on some of those. And the project is just started. I mean, started a year ago, but the real, the real project will start now for the next 4 years, where we have to do a lot of those demonstration studies. So we have a nice framework in place now, but yeah, now it's time to apply it and try to improve it. So yeah, we'll be in touch for sure.
Thank you, Carmine.
Andrea, I can see that you have raised your hand, please.
Yeah, can you hear me?
Yes.
Okay, hello. First of all, thank you very much for the presentation. I wanted to ask you, when you use the global earthquake model to assess losses, do you also include the effect of infrastructures, for example, transportation infrastructure, on the loss assessment, both in terms of, for example, direct losses, but also indirect losses?
So not yet, Andrea. So the losses that we included on the global model, it's only for commercial, industrial, and residential buildings, and only the direct damage. Okay, that's what I was mentioning before, that the impact from lifelines is still missing. We have, of course, studied the impact in a transportation system in specific studies. For example, we did a study for Messina in Italy. In fact, I don't know if you're Messina, but for example, in that case, we were studying how much is going to be, the disruption time and places which are going to be mostly affected. We also did the same thing for a mining industry in Portugal. Once again, what were going to be the losses due to the disruption, because these particular facilities, they're in places of very low seismic hazard, but they could have losses due to the disruption of the transportation system. But it's something we haven't included on the global model yet. In fact, this goes a little bit in line with what Carmine was also mentioning about the business interruption. A lot of these features are extremely, case study specific, right? The transportation system, the business interruption, and all that stuff. So despite the fact that you can find some studies out there which are fantastic, at the local scale, for example, for the San Francisco Bay Area and a few other places, if you try to extrapolate this at the regional, national, or even global level, sometimes things just do not work because of lack of data and the fact that the original models were developed for some parts. But I think it's where GEM just expects a little bit more that the community is just going to contribute with some of the models and use some of the open source tools to include that.
Mm-hmm. Yeah, I understand. How much do you think it will affect, let's say, the loss assessment in percentage? For example, if only considering buildings, you have, I don't know, 100%, how much do you think the impact of, for example, transport or lifeline losses would be?
Yeah, well, probably by a lot, and then it depends a lot. If, for example, if you see countries like Japan, I mean, yeah, we don't expect a lot of damage on the buildings, but you might expect some business disruption. And we've seen that in 2010, that the prices of the screens and electronics increased like globally because of the disruption in Japan. So it was not so much because of the direct damage, but because of the business interruption. For a few other places in the world, I think it might not be the case. For example, in places where you have a huge vulnerability, probably first you have the losses on the building stock. But I would say that for places like where earthquake resistance is a little bit better, you're going to have more losses due to the indirect losses and not so much due to direct damage.
Okay, thank you very much.
Thank you, Andrea.
Okay, we passed the hour, but if Vitor is still happy to answer some questions, if anyone has any question, you can raise your hand, you can write it in the chat. Meanwhile, one thing, the model that you were showing that you predicted the expansion of the cities, was it just land use in terms of like these will be residential, commercial, industrial, or was it a little bit more detailed that, okay, there is a chance that there will be 3-story, mid-rise, high-rise in this area? Was it detailed, or was it just, okay, the land use in this area will be changed and it will be some population over there?
It was very detailed, Arash, and that's actually that's a part that it's extremely important to incorporate in the model, because if you were just going to say this part are going to have some building there, this is not very different from you just increasing the losses based on how much you expect the GDP to increase, right? These models, you really need to incorporate the building classes, because maybe you can have urban expansion and the risk is not going to increase because there's tight design regulation. So you expect, you know, reinforced concrete, code compliant, modern buildings there, whose risk, at least in terms of percentage, will be lower. Or you can expect places where actually informal construction is still going to exist. You know, we have Adobe buildings, unreinforced masonry, and the risk is going to increase quite a lot. So in parallel with identifying the places which are going to be built now, the model is also going to basically start populating those built up areas with specific building classes. For that, we had to understand how was the census, you know, throughout the years, how we see, for example, Adobe and wooden buildings decreasing, and how we see, for example, other building classes increasing. We also included on the model the replacement of the buildings. So after a building has a certain amount of years, there's a likelihood that this building is going to be replaced. Okay, and usually, if it is in an urban area, you expect the building also to have, you know, more stories than, for example, what was there before. So this models, this particularities were also included. Let me just say, Arash, that obviously we don't produce one model. We produce hundreds of models because there's so much uncertainty there. So it's a huge Monte Carlo process to understand, you know, this is all the things that can happen with the same probability.
Very interesting. One other thing is, have you considered, I'm still in that machine learning environment. What do you think will be the reaction of cat modeling industry, insurance and reinsurance to that? Will they be happy, or will they see this as a proper threat, a competitor?
Yeah, no, I don't think they should see this as a threat. You know, I'm actually hoping they will see some of this as an opportunity. So, you know, first of all, of course, you know, the models that we have now, they work. I'm not saying that they do not work. They obviously work. I mean, the insurance companies and cat modeling companies have been using these models for more than 30 years, right? And I think we can all say that they've been quite successful, you know, given some of the companies. But for example, every time that an earthquake happens, a lot of times at GEM, we do receive requests, sometimes from partners, to help with the rapid estimation, okay? Or they just ask us, have you estimated this? So I think some of these models will be able to, you know, maybe show a different view. You know, I also think there's obviously extremely smart people in these cat modeling companies, insurance companies. So it's not just because we're gonna produce the science and publish that they will adopt this. I don't think that's going to happen. I think if this indeed works, okay, because we still need to prove that we're right. I think, you know, you almost don't have to convince them. You just have to put the model out there. And now on the next 5 years, if every time something happens, if your model indeed predicting something much better than the regular models, then that's it. You know, there you go. You have your proof to change some of the stuff that it's being done.
Sure, exactly. Very nice. I won't bother you more, and if you don't mind, I'll just share my screen for a second.
Sure.
So I'll just, again, thank you very much for attending today's session. Thank you to Dr. Vitor Silva for such an interesting discussion about the future, really the future of risk assessment.